This video is for those of you who may have a test on acids and bases, or if you just want to review this topic. So it's a list of multiple choice questions, and I recommend that you try these problems before viewing the solution. So let's start with number 1. Which of the following is a strong acid? Is it ammonia, acetic acid, sodium hydroxide, perchloric acid, or hydrochloric acid? Now you need to know the 6 common strong acids. These include HI, HBr, HCl, H2SO4, HClO4, and also HNO3. If it's not one of these acids, chances are it's a weak acid or something else. Now we could eliminate answer choice A. NH3 ammonia is a weak base, and B, acetic acid, that's a weak acid. Sodium hydroxide is a strong base. The right answer is D, perchloric acid, that's one of the strong acids. And E, hydrofluoric acid, is a weak acid. Now let's move on to number 2. The H3O plus hydronium concentration is 4.7 times 10 to the minus 3 moles per liter. Calculate the pH of the solution. Now there's a simple formula that will help us to get the answer. The pH is negative log of the hydronium ion concentration. So it's going to be negative log of 4.7 times 10 to the minus 3. Now if you don't have access to a calculator, what do you think the pH is going to be? What's the range of where it might be? So focus on this number. It's either going to be between 2 to 3 or 3 to 4. Now, if this number is greater than 1, pick the smaller range. So the answer is going to be somewhere between 2 and 3. So it's going to be B. If you type in negative log of 4.7 times 10 to the minus 3, this will give you 2.3279. And so B is the right answer for this problem. Number 3. The pH of the solution is 5.4. What is the pOH of the solution? Now you need to know that the pH plus the pOH must add to 14 at 25 degrees Celsius. So to calculate the pOH of the solution, it's simply 14 minus the pH of the solution. So in this example, that's 14 minus 5.4. 14 minus 5 is 9, and 9 minus 0.4 is 8.6. And so this is the answer. So C is the right answer in this problem. Number 4. Which of the following is the Bronsted-Lowry base in the reaction shown below? The Bronsted-Lowry base is the proton acceptor, and the Bronsted-Lowry acid is the proton donor. So notice that HF donates a proton as it becomes F-. So HF is the acid because it gives away a hydrogen. Water is the Bronsted-Lowry base because it accepts a hydrogen as it turns to hydronium. Now whenever you add a hydrogen to something, you create the conjugate acid. And if you take away a hydrogen, as in the case of HF, the result is the conjugate base. So the answer for this problem is water. Water is the Bronsted-Lowry base. Now here's a question for you. What is the conjugate acid of water? And what's the conjugate base of it? So anytime you want to write the conjugate acid of something, add a hydrogen. So H3O plus is the conjugate acid of water. And hydroxide is the conjugate base. To write the conjugate base, take away a hydrogen. So let's use ammonia for example. The conjugate acid is NH4 plus, and the conjugate base, take away a hydrogen, is NH2 minus. So with that in mind, let's say if we have H2PO4 minus. What do you think the conjugate acid and the conjugate base for this substance would be? So for H2PO4 minus, if you add a hydrogen, it becomes H3PO4. That's the conjugate acid. If you take away a hydrogen, it becomes HPO4 to the negative 2. So now you know how to identify the conjugate acid and the conjugate base of a substance. Number 5. The hydroxide ion concentration is 3.7 times 10 to the negative 4 moles per liter, or molarity. Calculate the hydronium ion concentration. Now, you need to know that water reacts with itself, and it ionizes. It turns into two ions. It becomes H3O plus and hydroxide. So this water molecule is the acid. Well, it could be either or, but actually, this one's acting as the Bronsellari base, because as it turns into H3O plus, it accepts a proton. This one is acting as the acid, because it loses a hydrogen, turning into hydroxide. So that's the Bronsellari acid. This is the conjugate acid, and this is the conjugate base. Now, if we write the equilibrium expression for this reaction, now these two are in the liquid phase, and this is in the aqueous phase, we know that K is going to be the products divided by the reactants. The products are on the right side, so that's going to be H3O plus times hydroxide divided by the reactants, which would normally be divided by water, but we cannot include any liquids or solids in the equilibrium expression. So this is known as the autoionization constant of water, sometimes referred to as the ion product constant for water. And at 25 degrees Celsius, this value is temperature dependent. It's 1 times 10 to the minus 14. So this is the equation that we need to calculate the H3O plus concentration. So it's going to be Kw, which is 1 times 10 to the minus 14, divided by the hydroxide ion concentration. So we're going to divide it by 3.7 times 10 to the minus 4. And so this is going to be 2.7 times 10 to the minus 11, which means that answer choice D is the answer. Number 6, the pH of the solution is 4.2. Calculate the H3O plus concentration. So here's the formula that you need. The H3O plus concentration is equal to 10 raised to the negative pH. So it's going to be 10 raised to the negative 4.2. And that comes out to be 6.31 times 10 to the negative 5. And so that's it for this problem. So answer choice D is the answer. Number 7. The pH of the solution is 9.5 at 25 degrees Celsius. Is the solution acidic, basic, or neutral? Now you need to be familiar with the pH scale. At a pH of 7, the solution is said to be neutral. When a pH is less than 7, it's acidic. If it's greater than 7, it's basic. So the pH of this particular solution is 9.5. So that's greater than 7. So what we have is a basic solution. Number 8. The hydroxide ion concentration is 2.6 times 10 to the negative 9 moles per liter. Calculate the pH of the solution. So there's different ways in which we could do this. Now what I'm going to do is calculate the pOH first, which is negative log of the hydroxide ion concentration. So that's going to be negative log of 2.6 times 10 to the minus 9. And so that's 8.585. Now the pH of the solution is going to be 14 minus the pOH. So that's 14 minus 8.585. And so that's 5.415, which we could round that to 5.4. So that's the pH of the solution. Therefore, B is the correct answer. Number 9. The concentration of H3O plus is 2.7 times 10 to the minus 4 in the solution. Is the solution acidic, basic, or neutral? Now here's what you need to know. If the concentration is greater than 1 times 10 to the minus 6 at 25 degrees Celsius, and we're going to assume the temperature is 25 unless specified otherwise. If it's greater than this number, the solution is acidic. If it's equal to this value, then the solution is neutral. And if it's less than 1 times 10 to the minus 7, we have a basic solution. So 10 to the negative 4, is that greater than or less than 10 to the negative 7? 2.7 times 10 to the minus 4 is greater than 1 times 10 to the minus 7. And you can use a number line. So let's say this is 0, this is 3, here's negative 4, and here's negative 7. As you go to the right, the numbers become greater in value. So negative 4 is higher than negative 7 because it's to the right. So therefore, what we have is an acidic solution, which means answer choice A is the right answer. Number 10, which acid is stronger? Is it HF, hydrofluoric acid, or HCN, hydrocyanic acid? And we're given the Ka values for these two acids. The Ka value for HF is 7.2 times 10 to the negative 4, and the Ka value for HCN is 6.2 times 10 to the minus 10. So given this information, how can we determine which acid is stronger? Now, you need to know that acid strength increases with higher Ka values. So the acid with the higher Ka value is a stronger acid. So it's not going to be C or D. Those reasons are the wrong reasons. 10 to the negative 4 is higher than 10 to the negative 10. So therefore, HF is the stronger acid, since it has the higher Ka value. Number 11. What is the pH of a 0.025 molar hydrochloric acid solution? Now you need to realize that HCl is a strong acid. So when it reacts with water, it goes to completion. So you should only have one arrow as opposed to two arrows. This is not a reversible reaction. And strong acids ionizes almost 100%. So let's say if we make an ice table, initially we started with 0.025. Now the reaction is going to go to completion. At the end, this is going to be 0. So the change is negative 0.025. And on the right side, the change is positive 0.025. So what we need to realize is that the concentration of H3O plus is the same as the concentration of HCl, which is 0.025. So therefore, we can calculate the pH of the solution. It's simply going to be negative log of the hydronium ion concentration, or negative log of 0.025. And so that is 1.6, which means that answer choice A is the correct answer. 12. Calculate the pH of a 0.75 molar hypochlorous acid solution. And we're given the Ka, the acid dissociation constant of HOCl. It's 3.5 times 10 to the negative 8. So what's the pH of the solution? Now hypochlorous acid is a weak acid, and so it reacts with water but reversibly. So for weak acids, there should be two arrows as opposed to one. And so it ionizes according to this equation. Now we need to make an ice table. So initially, we have 0.75 moles per liter of HOCl. And of the products, initially we have 0. So the reaction has no choice but to initially shift to the right. So the products will increase by X, and the reactant will decrease by X. Now let's add the first two rows. Now the acid dissociation constant, which is an equilibrium constant, is equal to the products divided by the reactants. Now everything is in the aqueous phase except water. Water is in the liquid phase, so it should not be included in the equilibrium expression. Now the Ka value is 3.5 times 10 to the negative 8. H3O plus and the hypochlorite ion, they're both equal to x. So x times x is x squared. And HOCl, the equilibrium value is going to be 0.75 minus x. Now, because the Ka value is very small, we could ignore this x. It's not going to be significant. So now let's cross multiply. So we're going to have 1 times x squared, which is x squared, and then 3.5 times 10 to the negative 8 multiplied by 0.75. So that's 2.625 times 10 to the negative 8. So now we can take the square root of both sides. So x is equal to 1.62 times 10 to the negative 4. Now notice that x is equal to the hydronium ion concentration. So therefore we can now calculate the pH of the solution. So it's going to be negative log of 1.62 times 10 to the minus 4. And so that works out to be 3.79. And so that's the pH of the solution, which we can round it to 3.8. So D is the right answer. Number 13. Which acid is stronger? Is it hydrochloric acid or hydrobromic acid? Now you need to know the trend for acids that is associated with the periodic table. So let's say this is carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. Acid strength increases as you go to the right and as you go down if these elements are directly attached to the hydrogen atom. So we're dealing with binary acids. So what you need to know is that HI is a stronger acid than HBr, which is stronger than HCl, which is stronger than HF. And HF is a stronger acid than water. Water is more acidic than ammonia, and ammonia is more acidic than methane. So clearly we can see that HBr is more acidic than HCl. So HCl is not the stronger acid. So the answer has to be between B and D. Now, electronegativity increases as you go up. So clearly, chlorine has a higher electronegativity value than bromine. So the reason is not due to electronegativity. The reason is due to size. A strong acid means that the conjugate base is very weak. So the stronger the acid, the more stable the conjugate base. Compare bromide to chloride. Bromide is a lot bigger than chloride. And because that ion is bigger, it has more volume to stabilize the negative charge. So because this ion is more stable, the acid is stronger. It's very easy for HBr to give off the hydrogen because it leads to a very stable product. And that's why HBr is more acidic than HCl. It's due to the stability of the conjugate base. So D is the right answer. HBr is the stronger acid because the bromide ion is larger than the chloride ion. And as a result, the bromide ion is more stable than the chloride ion. So the weaker the conjugate base, the stronger the acid. Number 14. What is the pH of a 3 molar ammonia solution? And we're given the Kb of ammonia. So first let's write a reaction. Ammonia is a weak base. And so it's going to react with water reversibly to produce the ammonium ion, that's the conjugate acid, plus hydroxide. So we need to make an ice table. So the initial concentration of ammonia is 3.0. And the products initially are 0. So the reaction is going to shift to the right, increasing the products by X and decreasing the reactant by X. So let's add up the first two rows. And the base dissociation constant, Kb, is going to be the products, which is NH4 plus, and then times hydroxide divided by the reactant, which is ammonia, NH3. Now we're given Kb, it's 1.8 times 10 to the minus 5. And so that's going to equal these two, which are both x, so x times x is x squared, and the equilibrium value for NH3 is 3 minus x. So if this value is large, and if this value is small, you could ignore x. And also, Kb is relatively small. So x can be ignored for this problem. So let's cross multiply. This is going to be 1 times x squared, and then 1.8 times 10 to the minus 5 multiplied by 3, which is 5.4 times 10 to the minus 5. Now let's take the square root of both sides. So the square root of 5.4 times 10 to the negative 5 is equal to 7.348 times 10 to the minus 3. So that's the value of x. And we can see that x is equal to the hydroxide ion concentration. So once we have the hydroxide ion concentration, we can easily calculate the pH of the solution. But first, we need to calculate the pOH. So that's going to be negative log of the hydroxide ion concentration. So that's negative log of 7.348 times 10 to the minus 3. And so the pOH of the solution, it's 2.134. Now to calculate the pH, it's 14 minus the pOH of the solution. So that's 14 minus 2.134. And so this will give you 11.866. And that's the answer. So we could round that to 11.9. And that's it for this problem. Number 15. What is the pH of a 1 molar sodium fluoride solution? And we're given the acid dissociation constant of HF. So fluoride is the base in this solution, and it's going to react with water. It's going to produce the conjugate acid HF and the conjugate base hydroxide. So once again, we need to make an ice table. So the initial amount of fluoride is 1.0. This is going to be 0. The products will increase by x, and the reactants will decrease by x. Now, because we have hydroxide in this expression, we need to use Kb for this reaction. However, we're given Ka, so we need to calculate Kb. Kb times Ka is equal to Kw, the autoionization constant of water, and Kw is 1 times 10 to the minus 14. So Kb is this number divided by the Ka value. So that's 1 times 10 to the negative 14 divided by 7.2 times 10 to the minus 4. And so Kb is 1.389 times 10 to the negative 11. So now we can write the Kb expression for this reaction. So it's going to be HF times the hydroxide concentration divided by fluoride. And so this is going to equal x squared divided by the fluoride concentration, which is 1 minus x. Now this number is very small, so we could definitely ignore this x value. So if we cross multiply, this is going to be x squared, which is equal to Kb times 1. Now let's take the square root of both sides. So X is going to be 3.727 times 10 to the negative 6. And so we can see that X is the hydroxide ion concentration when dealing with Kb. So now we can calculate the pOH of the solution. So the pOH is the negative log of the hydroxide ion concentration, which is 3.727 times 10 to the negative 6. And so the pOH is 5.429. Now the pH of the solution is going to be 14 minus the pOH. So that's 14 minus 5.429. And so the pH is 8.571. And so this is the answer, which correlates to answer choice B. So B is the right answer for this problem. Number 16. Which of the following substances is not amphoteric? So what does it mean for a substance to be amphoteric? An amphoteric substance is a substance that can act as an acid and as a base. Water fits this description. When water acts as an acid, it releases the hydrogen ion and turns into the conjugate base hydroxide. When water acts as a base, it acquires a proton, turning into the conjugate acid H3O+. So that's how you can tell if a substance is amphoteric. You have to ask yourself, can the substance give away a hydrogen and can it receive one? Now looking at answer choice B, this substance is also amphoteric. It can receive a hydrogen, turning into the conjugate acid H3PO4, and it can give away a hydrogen, becoming the conjugate base HPO4 2-. So the same is true for bicarbonate. It can act as an acid, turning into carbonate, and it can act as a base, becoming carbonic acid. Now sulfate is not amphoteric. It can behave as a base, turning into the conjugate acid bisulfate. However, it doesn't have any hydrogens to give away, so it cannot. There's no conjugate base for sulfate. So sulfate can only act as a base, and it cannot act as an acid. It can receive a proton, but it cannot give one away. So D is the right answer. This substance is not amphoteric. Number 17. Which acid is stronger? Is it chloric acid or chlorous acid? So this is a free response problem. Now you need to know that HClO3 is a stronger acid than HClO2. Both of these acids are known as oxyacids. They're acids that contain oxygen. And for oxyacids, as the number of oxygen atoms increases, the acidity goes up. So what this means is that HClO4 is more acidic than HClO3, which is more acidic than HClO2, and that's more acidic than HClO. Now, HCl is not part of this trend. In fact, HCl is stronger than the first three acids. HClO4 and HCl are considered strong acids, but HClO3, not exactly. It's like on the borderline. Now, some other examples are nitric acid, which is a known strong acid, and nitric acid, which is a weak acid. Sulfuric acid is a strong acid, but sulfurous acid is relatively weak. So as you can see, as the number of oxygen atoms increase, the acidity increases. So for this problem, HClO3 chloric acid is a stronger acid than HClO2 chlorous acid. Number 18. The pH of a 0.4 molar HX solution is 3.5. What is the Ka value of HX? So go ahead and try this problem. So HX is a weak acid. And like all weak acids, it's going to react with water reversibly, forming the conjugate acid H3O+ and the conjugate base X-. So as always, we're going to make an ice table. And that's a terrible looking E. And so this is going to be 0.400, and then the reaction is going to shift to the right, increasing the products, decreasing the reactants. So Ka is going to be H3O plus times X minus divided by HX. So H3O plus and X minus are both equal to X. So we could say that Ka is X squared divided by HX, which is 0.4 minus X. So if we could find the value of X, then we can calculate the acid dissociation constant Ka. Now we could find X by knowing the fact that we have the pH of the solution. And notice that X is equal to the hydronium ion concentration. To calculate the hydronium ion concentration, it's simply 10 raised to the negative pH. So that's going to be 10 raised to the negative 3.5. And so that's going to be 3.162 times 10 to the minus 4, which is equal to X. So we're going to take this value and plug it into this equation. And that's how we can calculate the acid dissociation constant. So it's going to be 3.162 times 10 to the negative 4 squared divided by the concentration minus that same number. And make sure to put these two numbers in parentheses. So the answer is 2.5 times 10 to the negative 7. So that's the acid dissociation constant for this particular problem, which means that D is the right answer. Number 19. The pH of a 0.25 molar weak base solution is 9.75. What is the Kb value of the weak base? So let's call the weak base B. It's going to react with water, and it's going to turn into the conjugate acid, which we'll call BH plus or HB plus, and then the conjugate base hydroxide. So if we make the ice table, this is going to be 0.25, 0 plus X minus X, and so forth. After a while, you just know what to do. So the Kb value for this reaction is going to be the concentration of the conjugate acid times the hydroxide ion concentration divided by the concentration of the base. So Kb is going to be X squared divided by 0.25 minus X. So the key is to calculate the value of X. If we could find it, we can easily calculate the value of Kb. Now we're given the pH of the solution. However, notice that X represents the hydroxide ion concentration. So we need to find the pOH first. The pOH of the solution is going to be 14 minus the pH, which is 9.75. So 14 minus 9 is 5, and 5 minus 0.75 is 4.25. Now that we have the pOH, we can calculate the hydroxide ion concentration. And we know it's 10 raised to the negative pOH. So that's going to be 10 to the negative 4.25. And so that's going to be 5.623 times 10 to the negative 5. So that's the value of X, which is what we need to plug it into that equation. So this is going to be 5.623 times 10 to the negative 5 squared divided by 0.25 minus X. So the Kb value for this particular base is 1.265 times 10 to the negative 8. And so that's the answer, which you could round that to 1.27 times 10 to the negative 8. So C is the right answer in this problem. Number 20. Which base is stronger, ammonia or methylamine? And we're given the Kb values for NH3 and CH3NH2. The Kb value for ammonia is 1.8 times 10 to the negative 5. And the Kb value for methylamine is 4.4 times 10 to the negative 4. So what you need to realize is that as the Kb value increases, the base strength increases as well. So the stronger base is associated with the higher Kb value. 10 to the negative 4 is higher than 10 to the negative 5. So therefore, methylamine is the stronger base. Number 21. The pKa values of 4 acids, HA, HB, HC, and HD, are 4.6, 2.5, 7.3, and 6.4. Which of these acids is the strongest acid? Now we know the relationship between Ka and acid strength. As the Ka value increases, the acid strength increases. So the stronger acid is associated with the high Ka value. Now what about pKa and acid strength? These two possess an inverse relationship. That is, as the pKa decreases, the acid strength increases. So the stronger acid is associated with the lower pKa value. So since we want to identify the strongest acid, we need to know which one has the lowest pKa value. And that's the second one, HB. So therefore, HB is the strongest acid. The weakest acid will be the one with the highest pKa value. And so that would be HC. HC is the weakest acid, HB is the strongest acid. So if you had to rank it, it would be HB, that's the strongest acid. The second strongest acid would be HA. It goes in order 2.5, that's less than 4.6, which is less than 6.4, and that's less than 7.3. Now 6.4 corresponds to HD, and 7.3 corresponds to HC. So we can see that HB is clearly the strongest acid since it has the lowest pKa value, and HC is the weakest acid because it has the highest pKa value. Number 22. Which of the following salts will produce a basic solution? Is it sodium chloride, ammonium chloride, aluminum chloride, sodium iodide, or sodium nitrite? Sodium chloride will produce a neutral solution. The pH will be around 7. Ammonium chloride will produce an acidic solution. The pH will be less than 7. When you place ammonium in water, it will react with water reversibly. It's a weak acid, and so it's going to create H3O plus and the weak base NH3. So because it generates the hydronium ion, it's going to produce an acidic solution. Now aluminum chloride also works the same way. The aluminum plus 3 cation acts as a Lewis acid. In fact, in water, it ionizes according to this equation. There's 6 water molecules attached to it, and it causes one of the water molecules to be ionized. So notice that there's 5 water molecules left, but one of the water molecules will lose an H+, and as a result, the charge on aluminum will change from +3 to +2. The total charge of the equation is +3. And so that's how the aluminum plus 3 cation creates an acidic solution. So metal cations with a very high positive charge are acidic in water. So for example, Fe plus 3 is another Lewis acid. It will create an acidic solution. Now what about sodium iodide? This will be neutral. I'm going to put A for acidic and for neutral, but the answer is E, sodium nitrite. It's a basic solution. When nitrite is put into water, it's going to grab a proton and form nitrous acid and hydroxide. Now here's a question for you. Can chloride react the same way with water and produce HCl and hydroxide? Because it has a negative charge just like nitrite. Can that happen? And the answer is no. Now let's talk about why. The conjugate base of a strong acid will not form a basic solution. However, the conjugate base of a weak acid will form a basic solution. You can write that down if you want to. Now, HNO2 is a weak acid. We know that. And the Ka value for that, if you want to look it up, is 4 times 10 to the negative 4. And keep in mind, it's not one of the 6 strong acids, so it's safe to say it's a weak acid. We know that weak acids react with water reversibly. So this will produce H3O plus and nitrite. So notice that nitrite is in this equilibrium expression. And the double arrow symbol means that the reaction can go to the right and to the left. So because that reaction is reversible, that means that if we place nitrite in water, it will react to form the conjugate acid HNO2. And so that's why we can say that the conjugate base of a weak acid will produce a basic solution. Because the reaction is reversible, it can go both ways. Now, the conjugate base of a strong acid will not produce a basic solution. Here's why. We know that if we put HCl with water, HCl is a strong acid, it ionizes completely. Strong acids should not have a double arrow. It's not reversible. So it only goes in one direction. Which means that if we put chloride in water, it's not going to form the strong acid. It's not going to happen. So to write this, that's supposed to be HCl and OH minus. This reaction will not work. So this reaction only goes towards the chloride ion. Chloride will not grab a hydrogen from water and turn into HCl. So make sure you understand that. The conjugate base of a strong acid will not form a basic solution, but the conjugate base of a weak acid will. And so that's why we can eliminate NaCl, because HCl is a strong acid, and NaI also because HI is a strong acid. However, this was the answer because HNO2 is a weak acid. So E is the right answer for this problem. Number 23. Calculate the pH of a 0.5 molar ammonium chloride solution. And we're given the Kb for NH3. It's 1.8 times 10 to the negative 5. So go ahead and try this problem. So ammonium chloride is an acidic salt solution, but we don't have to worry about the chloride part. Ammonium will react with water reversibly to produce ammonia and hydroxide. Actually H3O plus and the hydroxide. I take that back. This is an acid, so it's going to generate the hydronium ions. NH4 plus is 0.5, and this is going to be 0. And we know the reaction is going to shift to the right. And so this is how we can complete the ice table. Now, this reaction is associated with Ka because it generates H3O plus. So we could say that Ka is going to be the products, which is X times X, divided by ammonium, which is going to be 0.5 minus X. Now we don't have the Ka value for this reaction. We do have Kb for NH3, so we need to calculate Ka. Ka is going to be Kw, which is 1 times 10 to the negative 14, divided by Kb, which is 1.8 times 10 to the negative 5. And so that's equal to 5.556 times 10 to the negative 10. Now let's cross multiply. So we're going to have 1 times x squared, which is x squared. And because Kb is very small, we could ignore this x value. So it's going to be 0.5 times this number as we cross multiply. So 0.5 times 5.556 times 10 to the negative 10, that's 2.778 times 10 to the negative 10. Now let's take the square root of both sides. So x is going to be 1.67 times 10 to the negative 5. Now keep in mind that x in this example is the hydronium ion concentration. And so the pH, which is the negative log of H3O+, that's going to be the negative log of 1.67 times 10 to the negative 5. And so the pH of the solution is 4.78. And so this is the answer, which means that B is the right answer choice. Number 24. Calculate the percent dissociation of a 2 molar acetic acid solution. And we're given the Ka value for acetic acid. It's 1.8 times 10 to the negative 5. So I'm going to write acetic acid as HA. So like all weak acids, it reacts with water to create the hydronium ion and the conjugate base. So the initial concentration is 2. This is going to be 0. The products will increase by x, and the acid concentration will decrease by x. So we could say that Ka is going to equal x squared divided by 2 minus x. Now we need to calculate the value of x. So this is equal to 1.8 times 10 to the minus 5. And Ka is small, so we can ignore that x. Now if we cross multiply, this is going to be x squared, which is equal to 2 times 1.8 times 10 to the negative 5. So that's going to be 3.6 times 10 to the minus 5. And then let's take the square root. So x is equal to 6 times 10 to the negative 3. Now the percent dissociation is equal to the H plus concentration, which is the same as the H3O plus concentration, divided by the acid concentration, times 100%, which I'm running out of space. So the H3O plus concentration is the same as x. So it's 6 times 10 to the minus 3 divided by the acid concentration, which is 2, and then multiplied by 100%. So this is equal to 0.3%. And that's how you can calculate the percent dissociation of a weak acid. So B is the right answer. 25. The percent dissociation of a 0.25 molar HX solution is 0.13%. Calculate the Ka value of HX. So how can we calculate Ka given percent dissociation? Well, let's write the percent dissociation formula. It's equal to the H3O plus concentration, which is basically x, divided by the acid concentration, which is HX in this problem, times 100%. Now the percent dissociation is 0.13%, and the acid concentration is 0.25. So our goal is to calculate x. To do that, we need to multiply both sides by 0.25 divided by 100. So on the left side, it's going to be 0.25 over 100 times 0.13. On the right side, these two will cancel, and these two will cancel, giving us x. So x is going to be 0.25 times 0.13 divided by 100. And so that works out to be 3.25 times 10 to the negative 4. So now we could calculate Ka. So let's write the reaction associated with this problem. So this is 0.25. This is going to be 0. And then you know how to finish it at this point. So clearly we can see that Ka is going to be x squared divided by the reactant, 0.25 minus x. So let's take this answer and plug it into this equation. So Ka is going to be 3.25 times 10 to the negative 4 squared divided by the acid concentration minus x. And so Ka is going to be 4.23 times 10 to the negative 7, which means that E is the right answer.